Hi, we're going to solve this buffer problem. And before we solve this buffer problem, I would like to read it out loud and make some mental notes as I read through this problem. So the problem states a buffer contains 0.020 moles of lactic acid, and the Ka for lactic acid is given to be 1.40 times 10 to the negative 4, and 0.050 moles of sodium lactate per liter. Calculate the pH of the buffer. So anytime you're trying to solve a problem, important thing is as you read the problem, make note of all of the information that's given there, and then we can make a note of what we're asked to figure out. Okay. So the first thing that we're going to document is what is given. So if you pay careful attention, you will see that the information that's given are, first of all, it says that your buffer contains 0.02 moles of lactic acid, and it just doesn't say it's mole, and you won't get the feel that it's actually talking about concentration of lactic acid until you get to the end of the statement where it says it contains 0.02 moles of lactic acid and 0.05 moles of sodium lactate per liter. So whenever you're expressing moles present in a liter, then we're going to say that that is concentration. So that's why when I made a note here, I put things within square brackets because we are representing that as concentration. Okay, and also pay attention to the units. I've written it as 0.020 moles per liter. So that's for 1 liter. And we know that lactic acid is an acid, and we're making a buffer. So it should be a weak acid because we know that the two key ingredients in order to make a buffer, one is weak acid, the other one is the conjugate base of the weak acid. And right over here in the problem, it gives you the Ka information. So we've written down the Ka information here. Ka is 1.40 times 10 to the negative 4. And then we have sodium lactate concentration. So sodium lactate concentration is also written in square brackets. And sodium lactate is the conjugate base or the salt. So we've written that value as 0.050 moles per liter. Okay, so we've written all the given information. Now we're going to document what we are asked to calculate. What we are being asked to calculate is the pH of the buffer. So we have to figure out the pH of the buffer. So given all these parameters, we are given the concentration of weak acid, we are given the concentration of conjugate base, we're given the Ka of the weak acid, and we're asked to calculate the pH. And we have to think what mathematical relationship or what kind of things that you've learned in the past that helps you connect all of these parameters. And if you think about it, it'll tell you that the equation that we've come across that connects all these parameters is the Henderson-Hasselbalch equation. And in the Henderson-Hasselbalch equation says pH equals pKa plus log of concentration of conjugate base or salt divided by the concentration of weak acid. And we also learned that if you want to figure out the pKa, what we need to do is take the negative log of Ka. And if we are able to do that, then we can actually very easily solve this problem. So in the next step, we're going to set up our calculation. So here's our strategy and here's our calculation. So in the calculation, what I've done here is I've first calculated the pKa for the weak acid. So for calculating the pA, I've used negative log of Ka. So in the place of Ka, I've substituted 1.40 times 10 to the negative 4, and I've taken the negative log of that, and then I got 3.85 for pKa. So now I have pKa value. So this pKa value that we've calculated here can very easily be plugged into the pKa in this Henderson-Hasselbalch equation, and then we can plug in the rest of the parameters into these variables right here. So here is our Henderson-Hasselbalch equation. Here is our pKa. Here are the concentration terms. In the place of pKa, I have substituted 3.85, and then in the place of the conjugate base concentration, I have substituted 0.05, which we wrote down in the previous slide for sodium lactate, and then 0.02 for the lactic acid concentration. So I plugged it in here, and then we're going to simplify this particular equation further. So what I did here is that first simplified this fraction, 0.05 over 0.02. I changed that into 2.5, and then I took the log of that, and then that gives us 0.398. And then this 0.398, when added to the 3.85 that we calculated in the previous step, gives us a final pH of 4.25. So this is the final pH of the buffer. pH of 4.25 is the final pH of the buffer. Okay.